Thanks for the introduction, everyone, and thank you everybody for coming. We've sort of crossed wires here where lots of people are back in the States for ICRA, and I've come over to ETH for this talk, so thank you for coming out today. Like Amon mentioned, I'll be chatting today about some approaches that are helping us to expand the mission profiles that we can pursue in extreme environment and space robotic autonomy. And I'd like to preface this with a bit of motivation that I'm sure many in this room are already familiar with. But a recurring theme in robotics in recent years is starting to move the robots out of the lab and put them into the field, where we encounter stochasticity. Things aren't perfectly controlled. We might not know our own dynamics models. We might not know the environments we're entering a priori, where things aren't very tightly controlled. And so as robots enter these dynamic, uncertain environments, we have to seek out approaches that can handle these uncertainty sources that traditionally we are not dealt with in our robotic planning and controls algorithms. And as we enter these challenging environments, autonomy's job is to allow us to tackle these complex mission scenarios that might be too difficult for a human to operate or teleoperate. It might be too dangerous. We might seek safety guarantees that we can't otherwise provide with a human operator. And that's where autonomy comes in. And if we can provide these items, then we can pursue these more agile, difficult mission scenarios. Things like autonomous rendezvous with tumbling targets, which we'll get to in the talk today. Exploring very challenging dynamic environments where you're making and breaking contact, you're having difficult physical interactions with the environment, or cases where you just don't know your maps a priori, which we'll talk about a bit for our Cadre lunar rovers, where you don't have complete environmental knowledge beforehand. You send your system to the field and you have to figure out how the planning and control can tackle that situation. So one motivation for these extreme environment robotics, for autonomy in these extreme environment robotics applications is round trip light time. And this is particularly important for me as we're thinking about exploring ambitious and further off areas of the solar system. And this is the amount of time it takes for a signal to reach a source and come back, accounting for typical delays. So for the moon, this is about 3 seconds, possibly teleoperated, but if you have faster dynamical interactions, autonomy can really benefit you. If you're talking about Mars, then now you're getting into tens of minutes potentially in that round trip time, which can be very wasteful if you constantly need to have a human in the loop. And then if we're getting to other areas further off in the solar system, like the potential ocean world Enceladus, now we're on the order of hours. So autonomy really becomes important if we want to explore any of these regions. Now, one question is why are we looking at increasing levels of autonomy now for these systems? One answer is that the compute that we're willing to put on these typically resource-constrained systems is still resource constrained relative to other areas of ground robotics you might see, but more capable than we've ever seen before in a space robotics domain. So for example, on the Ingenuity Mars helicopter, we have a Snapdragon 801 processor that's approximately equivalent to a circa 2013-14 cell phone grade chip. And this means we can have compute that is fairly computationally efficient per power efficiency. So one metric for that is DMIPS per watt. So this is a measure of computational capability per power input for some of these processors that are getting flown on some of these space robotic systems. And here's a little visualization to help with that. This is the RAD 750 processor. So this is the volume here roughly corresponds to that DMIPS per watt from the previous slide. So this is the area here is that DMIPS per watt for RAD 750 that we might find on the Curiosity rover and many other missions that have been launched before. This is the DMIPS plot of the Snapdragon 801, which is powering the Ingenuity helicopter, which recently ended its mission, but operated successfully on Mars for a number of years. And this is the onboard dual and ARM processor on the Astrobee robots, which are a set of free flyers on the International Space Station, which we'll talk about a bit more today. So the compute capability is getting on par with what we see in some of our more traditional ground platforms. And this is opening up a new set of autonomy algorithms that we can begin to put onto these robots that allow us to enter these more agile situations. So my interests in what the lab looks at back at USC as I'm getting things set up over there is autonomy for these space and extreme environment applications. So we have many challenges here. We started talking about some of those, but we often have imperfect model or environmental knowledge. We might not know our set of dynamics perfectly. We might not know our interaction with the environment perfectly. We have more capable, but still compute constrained processors. So we have resource constraints we have to deal with. We often have strict safety requirements for space and extreme environment robotics applications. So we care about safety and robustness guarantees where we can find them. And we're often dealing with dynamically complex systems when we're interacting in these environments. But if we can solve these challenges, we gain all those advantages we talked about previously. We can operate in some of these more agile scenarios. So today I'll talk about a few examples from the microgravity robotics domain. This is when we are in microgravity in orbit around the Earth, and we're trying to operate in proximity to some other robot or structure or some sort of interesting constraint violation that could occur. And planetary and lunar surface robotics. So I'll also talk about our Cadre lunar rovers, which are launching to the Rainier Gamma region of the moon. And so again, the lab is particularly interested in bridging the gap between theory and practice. We're strongly motivated by some of these application scenarios I've just highlighted, developing the theory to solve the challenges that arise from those scenarios, and working through finding where our assumptions break in the theory, and then going back and figuring what we have to tweak on the theory side to make things work. And I'm sure many of you are familiar with the robotic motion planning problem, but I'll overview things here just to sort of frame some of these scenarios. So robotic motion planning is a key piece of the autonomy puzzle in guiding these systems through these uncertain environments. We typically have a cost function where we specify different objectives we would like the agent to obtain. We have a set of system dynamics, often ordinary differential equation that constrains how the system is allowed to move around. We have some initial starting conditions where we require the system starts off, often a goal set we'd like to reach, a set of state constraints that we must remain within, a set of input constraints we must remain within. And so a very typical example is we're trying to navigate an environment, and you have some obstacle set you want to avoid as one of these state constraints, and you have a goal region you want to reach. And so obeying your system dynamics, you want to go from A to B. That's in a nutshell the robotics motion planning problem. Now, this problem can get increasingly interesting once you start to go from the deterministic realm to the stochastic realm. One form of this problem we'll talk about today in a few examples is where we have parametric uncertainty within our system dynamics. So this is often a form of epistemic uncertainty. It's uncertainty we consider resolvable within our ability to model. And we'll also talk a little bit about some of this aleatoric uncertainty, this noise uncertainty beyond our system modeling capability. And traditionally, we want to remain robust against that uncertainty. This is a challenging problem. We're talking about belief space planning. We're dynamically constrained. We might have challenging kinematic constraints like non-convex obstacle sets. So this is a hard problem, which typically invites approximate solutions. So again, we were talking about two different types of uncertainties there. We can have this learnable epistemic uncertainty. And you might imagine, for example, if you were a robot and you grappled a package you didn't know about, you might learn a parameter like mass, for example. We might consider that within our modeling capability. It's a parameter that we can learn. And so that's epistemic uncertainty. It's something we can learn along the way. Now, you might also have this unresolvable uncertainty, aleatoric uncertainty. It's this very common, there's different representations, but a very common way of representing it is as a bounded additive set onto your system dynamics. And when you're talking about this form of uncertainty, you're usually seeking a robustness guarantee so that you can operate despite having this disturbance to your nominal dynamics model. So we'll touch on a few elements of robust plan and control, thinking about information-aware planning. So how can you gain some of that information, for example, in your system parameters along the way as you're operating, as well as thinking about how to make this real-time on resource-constrained systems that we're typically dealing with in these extreme environment robotics applications. So we'll talk about three approaches here. We'll start off in the microgravity robotics domain. We'll talk about autonomous cargo manipulation. Then we'll move on to autonomous rendezvous. And then finally, we'll move on to our Cadre lunar rovers, and I'll discuss an approach for the first model predictive controller. We'll run another celestial body, so go MPC. So we'll start off first with Rattle. Rattle is an approach to deal with the information-aware form of this problem when we had that epistemic uncertainty that we are considered within our modeling capability. The basic idea is that you have an information-aware planner that can trade off incentivizing information gain against your traditional objectives of reaching some goal, minimizing input usage, for example. And incentivizing the information gain explicitly can help introduce motions that let you learn about your own system dynamics model as you move around. Rattle combines this into a framework where you use this latest learned information to inform a robust tube MPC that can provide some robustness guarantees relative to your current understanding of the uncertainty in the system. So let's break this down a bit. There's a high-level planner that's doing the guidance with some nominal system model. The local information-aware planner, this is where things get interesting, and this is where you're thinking about that trade-off problem of trying to gain information while also reaching your goal. And at this lowest level is this robust model predictive controller that's using the current uncertainty bounds to provide robustness for your system. So we'll focus here on the information-aware portion of that problem. Here again, we have our motion planning problem stated again. And so this is familiar from before. We can discretize this continuous problem and use numerical optimal control to repeatedly solve an optimization problem online. This is known as model predictive control. I'm sure many here are familiar. Model predictive control allows us to take the best input from the current understanding of the state from the system model and your current state inputs, and apply that input and repeatedly recompute the best inputs you can apply to your system. Now, what we need here is a notion of information awareness. We need some sort of information metric to incentivize that information gain. One way to do this is to use something called the Fisher information. So Fisher information is basically a measure of how informative certain motions are about parametric unknowns within your system model. So if you're maximizing Fisher information, you're essentially decreasing the lower bound of what's known as the Kramer-Rao lower bound. So the best possible floor that you can get for your estimates of your system parameters. And so again, these are parameters within your system dynamics model. This is for a particular type of uncertainty that you're trying to incentivize. that Fisher information can be discretized and used as another trade-off term within your cost function. So now we're thinking a bit about, you could think of this as sort of the exploration exploitation trade-off. We have an information term and we have these traditional terms that we expect in our model predictive control cost function. So this trade-off term allows us to selectively choose information content in our trajectories as we move around. And so this problem comes up in the cargo manipulation problem. So this basically on the space station, the resupply capsules periodically come up with these large payload bags that are full of objects, but we don't know the exact inertial properties of those objects. So as the robots grapple those objects and then reposition them around the capsule, they would benefit from having a more precise dynamics model of that system so that they can handle those parametric unknowns. This is just a simple granite table example here where we have select a manually tuned decreasing weighting on that parametric information gain for the IZZ moment of inertia. So at left is non-informative. There's no additional incentivization of learning about the IZZ moment of inertia. And at right, there is a weighting on that value, but you're also trying to go to some waypoints along the way. So you're going where you need to go, but you're also introducing some excitation as you get there. So introducing that extra excitation results in a lower covariance at the final state after this prescribed waypoint motion. So you're saying, go where I want you to go, but add some excitation along the way. The result is you have a better understanding of that single system parameter in this example. So let's scale this up a bit to 6 degrees of freedom. So this is now Rattle operating for this payload manipulation problem where you want to go from A to B, and you have a global planner operating with the current understanding of the system model, producing a reference plan in red. And then you have this local planner that's information aware. So that information awareness is the MPC that's continually replanning with a adjustable level of information content as you progress along the trajectory. And so there are different ways to choose this information content. These are a few heuristic examples where this is pre-assigned by a human beforehand. This is an information term on, for example, one of those parameters in your system dynamics. So you can adjust that value in different ways. You can assign learning about parameters at a particular point in your trajectory where you expect it might be useful. So this is all a bit heuristic and pre-assigned. So you'll see here, for example, there's this decreasing weighting as you move along. Initially, you have this extra rotation that's helpful for learning about your moments of inertia. And as that weighting goes away, you just have more translational motion instead, rather than that extra rotational excitation. So this is one example demonstrated on station of, at left, the non-informative motion, where you're just doing pure translation. You're not learning anything about your moments of inertia or any of those rotational parameters. And at right, there's a bit of extra excitation to allow you to learn more quickly about your mass and moments of inertia. And so those are just what those plans look like from the videos. So you can see for the informative plan, you have this extra rotation intentionally added in selectively along the path that allows you to deviate a little bit while still constraining the system. The end result is that this trajectory is more informative. So this is a plot of the total information gain across 3 or 4 relevant parameters rather. So this is information content for mass, and there are 3 moments of inertia here. The solid black is the case where you add in that information weighting. So you want the system to excite a little bit along the way, and the net result is more information content. So these values are higher, which we expect because we're exciting the system as we move. And the net result is that the covariances and the means of our parameter estimates for those values we care about are a bit lower. So this is a non-informative trajectory here. You can see, like, for example, for the IXX moment of inertia, we converge to a totally incorrect value. It's not even within standard deviation or two of our variance for that parameter. But we converge quite nicely when we have this selective information assignment. So there are other ways we can assign this trade-off. So that previous result was for a pre-assigned heuristic where you anticipate needing information at certain times. A potentially more sensible way to do that is to basically get feedback on the current model knowledge. So we can use the current covariance on your parameter estimates as feedback on that weighting in your cost function. So you say, if I'm very certain about what's going on, I care about my system model, I care less about that excitation, I won't excite as much. So this starts to automate that process so that you don't have to have a human pre-assign when the information content is important. And so here's an example of that. We can look at, for example, right here for the IXX moment of inertia. So this is the convergence of the parameter. Eventually, once our variance gets small enough, we reach a cutoff point where the total information content planned by the MPC's replanning is shut off, and we're now just doing, we're basically turning off that information term in our cost function. But along the way, we have a selective amount of information content. You can see the relative weighting changing here, tied to the variance of that parameter estimate. So as we're more certain, we care less about learning about a particular parameter, and we tune it down in the cost function. And finally, I'll briefly mention the robust control portion. So as we learn about those system parameters, we still have uncertainty within the system model in terms of the uncertainty over the variance in those parameters. We still want to remain robust to that. So robust tube model predictive control, which some of you might have run into in your coursework here and research as well. Robust tube model predictive control basically says I can provide a guarantee that for those perturbed dynamics, for the remaining level of uncertainty in the system, I can construct a bounded set on that additive bounded set on the uncertainty added onto the system dynamics. And I can construct a guarantee that in the future, I will only evolve within a tube centered on my nominal system trajectory. And you're moving your nominal system trajectory around in this optimization. So basically, any leftover uncertainty, those aleatoric terms from the parameters you hadn't estimated, can then be controlled with that robust tube model predictive control. This is just one example. So this is not running the information-aware portion. This is just robust tube model predictive control tracking with a standard MPC at left and a robust MPC at right. And this is just the dominating uncertainty source here is actually the localization system of the robot itself, which is fairly noisy. So there's an assumed additive bounded noise term that's accounting for that. And this is at left, this is the trace of that trajectory, and this is the one at right. And we have smaller RMSE and smaller maximum deviations when we're using robust tube model predictive control, which we expect. So, so robust tube MPC can be a useful tool in not just these microgravity robotic scenarios, but in general, as long as you can construct the reachable set approximation that shows how you'll evolve into the future. And so one other important aspect here is with Rattle, you are updating the uncertainty bound online. So likewise, if you can update the reachable set approximation online, you can ease off that conservativeness in the tube model predictive control. You're more certain about your system model, which means you're more certain about the size of the reachable set that you will evolve to in the future. And this lets you get a little control authority back. You don't have to reserve as much of your control inputs to counter potential disturbances you'll see along the way in your ancillary controller. Okay, so now we'll jump over to trace, and we'll go through trace relatively quickly, just so I can give some time to discuss Cadre. Trace is a framework that allows us to perform autonomous rendezvous with tumbling targets. There are a number of these targets on orbit that are high value, they're high volume, high mass, and if we don't rendezvous with them to fix them or deorbit them or service them, they could be a problem for future orbital debris creation. So a number of these targets are tumbling, and we don't know their tumbles exactly. So we have that uncertainty bit rising up again. Trace is an approach that demonstrates the full pipeline of observing this tumbling target, estimating its tumble state, and in some cases, its inertial properties as well, producing the motion plans to reach it for the estimated state, and tracking that state with a form of robust tube model predictive control, thinking about the uncertainties in the tumble of the target. So I'll have a little graphic in a moment that helps discuss that. So there's this chaser vehicle and the target. The chaser is observing the target. The target is tumbling, but we don't know its tumble. We can produce a estimate of the target's state that will then evolve with the new Euler dynamics. It's so that we could know its future tumble. That state estimate is not perfect. It comes with a covariance matrix on the state estimates, right? So because we don't know the target state perfectly, we end up having this problem of if we planned a deterministic trajectory to reach the target could be in some different future state. So you could think of it, the uncertainty arises in a pretty interesting way here. It's not uncertainty within your system model, it's uncertainty within the target's future evolution. And you have planned a trajectory in that target frame for a variety of reasons, mostly collision constraints are a lot easier to represent. But you've planned a trajectory in that target frame, and that trajectory could be at different points in the future. So you're trying to counter the potential shifts in the target reference trajectory as you get better information about its motion as you move along. You can again use robust tube model predictive control in this example for that unique form of uncertainty. You're basically trying to capture the future target updated trajectory in the inertial frame within your reachable set. And you want to say that you can always capture it so that you'll always be able to reach that that trajectory that you've planned that's avoiding obstacles in the rotating frame. So I'll just skip to the videos here. So trace has been demonstrated on orbit. We have here are estimating the chaser's tumble. We're getting an estimate of the state using some factor graph-based methods. We have uncertainty on that state, and then we're producing a nominal reference trajectory, and then using robust tube model predictive control to track that reference trajectory with the online state updates of the target's tumble. The end result is that we are in this standoff phase where we're now close to the target, and we could then do some sort of docking maneuver, which is work that the lab is starting to look at now as we get some proposals out over the next year. And here's another one. I'll just show this video quickly, and then I'll jump over to Cadre so we can discuss MPC a little bit. So same problem. The chaser has a tumble. The target doesn't know it. The target estimates that tumble, produces a nominal reference trajectory, tracks it with robust control to account for shifts in the reference trajectory as we get better target estimates along the way. Okay, and now I'll talk about Crescent, which is a real-time model predictive control approach for the Cadre Lunar rovers that are launching to the moon likely in 2026 now. I'm waiting on our launch provider. So I'll briefly overview Cadre first, and then I'll get into the actual approach. So Cadre is a set of multi-agent lunar rovers that are fully autonomous. Each of them is running a full modern robotics autonomy stack. They're doing their own mapping, their own localization, their own planning. They are multi-agents, so they cooperate with one another. They perform distributed leader election to determine who's in charge at any given point. And these sort of multi-agent systems will enable new forms of science and data collection that we can't do with our traditional single-agent approaches. We can be in more places at once. We can be a little riskier with the missions we attempt. If we lose one of the agents, we have resiliency and redundancy. We can continue the mission. Basically, this opens up a whole new set of science objectives we can accomplish for these extreme environment robotics scenarios. Cadre is launching to the Rainier Gamma version of the region of the moon. So if you look up at the moon at night and it's not waxing or waning, you can see the area we're going to here, sort of near the equator on the western side. Cadre will be equipped with a set of ground penetrating radar to perform multi-static measurements to get a picture of the lunar subsurface. For example, we might encounter some lava tubes, but we'll have a better idea of what's beneath the lunar surface down to a few tens of meters at most. So there's two main goals for two main modes of operation for Cadre. One is exploration mode. So in exploration mode, we're basically doing a max coverage problem. We have a region that we don't know beforehand. We don't have any a priori information about the region we're going to. The best knowledge we have is roughly meter scale, and our rovers are about 20 to 30 centimeters or so in length. So the orbital imagery we have doesn't help us very much in terms of navigating the environment. So we're basically doing this mapping entirely without a priori maps. The exploration phase is assigning waypoints to efficiently cover this area as fast as possible. And from a single agent level, this means that we have to get to waypoints in a min time problem and obey various constraints like avoiding obstacles we observe along the way, obeying our rover kinematics, et cetera. We also have a distributed measurement phase. So this is for our science goal, where we have those ground penetrating radar, and they need to maintain a baseline relative distance relative to one another, or a distance relative to one another as they move along. So that distributed measurement objective then introduces another interesting constraint on the system where the rovers have to move through the environment, but also maintain a constraint relative to one another. But they also have to deviate because they're going to make obstacle observations that they didn't have beforehand. So you have all these competing constraints and you get this highly constrained planning problem. So Cadre at a single agent level then is planning among this unknown obstacle set with objectives sent from a higher level team planner planned by a single rover. Those waypoints are then sent out to the individual rovers. And the approach divides up the planning into a multi-level planning problem. So there's a global and a local planner. The global planner deals with the long horizon, more like mid-horizon really, but how do I avoid what's in front of me for the next few meters? Getting to waypoints I want to get to. The local planner is acting more like a traditional model predictive controller, doing higher rate control, accounting for disturbances as you move along. And so we have again, our motion planning problem pops up, where we have our objective problem, we have our dynamics constraints and other equality and inequality constraints that we want to assign for this particular problem scenario. So the key challenge with Crescent is we don't have our maps beforehand. So there's a difficulty here. You can either be very pessimistic or very optimistic. If you're very optimistic, you have an unknown area and you assume that it's completely safe. This is fine for planning initially until you get close to constraint violation. Maybe you observe an obstacle when you're very close. Maybe you're approaching a negative obstacle, for example, a crater or a small cliff wall that you hadn't seen before. And if you take the optimistic approach, you'll find yourself in an unrecoverable situation when it's already too late. So this is one of the key advantages of the multi-level planning. The global and local planner can actually have different planning problems, where the global planner is optimistic, allowing you to make forward progress. The local planner, which is operating over shorter horizons within which your perception system will probably have seen the obstacles already. The local planner can operate with a more pessimistic view of the world with a different map representation. So in our case, we actually have two versions of the map, one with this optimistic version for the global planner, another with the pessimistic version for the local planner. This allows you to stay safe in cases where you don't get those observations until you're very close, but it also allows you to be aggressive enough in the planning that you're not locked in and doing nothing for the entire time. In our case, we're using a nonlinear least squares solver, so to deal with the highly constrained nature of this problem. And so these constraints are actually all turned into penalty terms in the cost function. And so we have, for example, our vehicle kinematics, our driving constraints, all those various safety constraints I talked about. In some versions of the problem, for the example, the exploration problem, we have min-time timing constraints, or timing cost rather. But for the distributed measurement problem, we actually have timing constraints. So we want to be at each of these particular points at a particular time, because if we're there on time, it means we're in formation. So we have these many constraints we need to throw into the problem. And so again, just highlighting that these differing approaches to treatment of the map means we have two competing planning problems. So we need to, this means that we sometimes need to do replanning on the global planning level as you're getting updates to your map information. You might have plans that are invalidated. You might have observations that don't mesh with the representation that the local planner has. So replanning is very important here to make sure that both planners are sort of converging to a similar map representation of the world. And I just have a few videos of the MPC approach running. So this is in the Mars yard over at JPL. This is just a sample navigation in a cluttered obstacle field. So this is a bit more cluttered than the region that we expect to reach in Rainier Gamma. Let's play it again. So even in these in these very dense environments, we can still successfully navigate with this tiered approach. And as I'll show in a moment, we're able to compute solutions in real time that meet rates that we require for our system. And we have fairly high success rates, even with higher cumulative fractional area rock coverage, both negative and positive obstacles. And I'll note that some ongoing challenges for these systems are in thinking about the perception system itself and things that you can never observe. So one particular problem is shadowing. Shadowing is particularly an issue during lunar dusk and dawn, when you have these very long, dark, stark shadows. Because we're a stereo-based system, we basically don't get any feature observations in those regions, and they're permanently unknown. So this means you permanently have a different representation at the local and global planner levels, where the pessimistic version is trying to avoid that region, and the optimistic version is trying to traverse through it. And there are also limitations in perception because we're so low to the ground here. So typically in these extreme environment robotic systems, you often you have limited sensor suites, you might have limited fields of view, and this is very much the case in our situation where we have dual front rear stereo, but it's very low to the ground. Typically, you would try to mount these cameras as high as possible to see as much as you can. But we're only revealing a little bit of the environment as we move. So a prime area for future investigation is thinking about how to couple the capabilities of your perception system, particularly if it's a very limited one, into the planning problem. So you're not wasting time later on. These are just a few of the runtime examples. So this is Monte Carlo, where we don't have a hard guarantee on runtime, but we can pretty happily bound it probabilistically over a range of difficult problem scenarios. So these are just some of the parameters of the problem that we're solving. So these are roughly 40 time step horizons, and the system state is, I think we're about seven DOF here, with a large number of constraints for this nonlinear least square solver. But we are running on real time on a resource constrained processor on these rover systems. And let's show one more sort of fun video here. So this is that nighttime navigation. So these regions are very difficult. You don't get any feature observations here, and they're perpetually unknown from a map representation standpoint. So this is just a traverse around some an obstacle field here with negative, positive obstacles and lighting for lunar night, or rather lunar dawn. And so this is using the planner for the single agent fully autonomously, just with a small set of waypoints and the corresponding constraints that it might have been given, for example, for that distributed measurement task. And this is an example of an exploration task. Again, this is that sort of max coverage problem where you drop the safety constraints on staying within a set boundary and arriving on time, and instead you're trying to move around as fast as possible. So I'm very excited about the motion planner on Cadre, and looking forward to it flying in the next few months, years maybe, but looking forward to it flying soon as we start to pull these planning control algorithms into increasingly more complex scenarios. I had a few more slides here where I sort of pontificate on where we need to look next in the field, but we're running a little low on time, so I'll sort of skip these for now and to leave a little time for questions. Yeah, looking forward to chatting more, and I know I'm meeting with some of you later in the day as well. So thank you very much for your attention, and happy to answer any questions. Yeah. Sure.
I'm not really familiar with the specifications, but I do know that there are several scattered applications for space, and I would imagine that if you have a better time-long payload, it would introduce a time delay in addition to changing the parameters of the dynamic system. So first, I want to know if you tested the Rattle with better payload or something, or would introduce a time delay in addition to the change, or if it's even a relevant application for that.
Yeah, you said tethered, or tethered rather, or yeah.
And it's not tensioned, then you would not have a response.
Yeah, right.
And then because you're doing an excitation to get a response, it would maybe have a time delay.
Yeah.
Is this something that you tested?
Yeah. So I haven't looked at time delay systems for this approach. As long as you can represent your unknowns parametrically within your system dynamics model, you can apply Fisher information as a metric within your cost function. the time delay aspect is interesting. So basically, you're saying if you apply an excitation, you don't get a meaningful result back out of the system until sometime much later. This, I need to check my assumptions again. I think this would still fall within the bounds of the approach, but one of your limitations is going to be the time horizon over which you're planning. I sort of glossed over that detail here, but when you discretize the real continuous problem you're trying to solve, you end up setting a time horizon on the model predictive control trajectory optimization problem that you're solving. So the information content you gain has to fall within that time horizon, or you get no reward. Yeah, it's the delayed reward problem that also comes up in reinforcement learning. So would definitely be interesting to think about. I have to think about it more now. And I'll also add another question I sometimes get about this approach is if you have like flexibility within the payload model, harder to model nonlinear effects. So as long as you can represent your unknowns parametrically, this approach can tackle them. Once you start getting into like additive unknown residuals, then you have to start looking for other approaches, particularly if you're trying to target information content. Yeah. Yeah, exactly. Yeah. Yeah. Yeah, you could incorporate that form of information metric into the optimization with those. Yeah. Mhm. Yeah. Yeah.
Question from the Rattle. So the Fisher information matrix, it depends how do you propagate the information from the state into that matrix, or how this inside the controller, I guess
you need to solve an additional ODE. So there's another another integration you have to perform. It increases your the number of it basically doubles the number of decision variables in the problem as well. I can point you to the paper. I don't have it in the slides, but I can point you to the paper that has the discretization here, which is that part is actually not my approach. That's from that's another piece of work we built on, but I can forward that to you. Yeah. Yeah. Yep.
So in theory, we know that by changing, for example, online changing the cost function between resolving the MPC problem or changing, for example, the minimal RPI set as you do based on online measurements, this could, in theory, it could lead to loss of stability or loss of feasibility of the problem. So
yes.
Yep. Take care of it, or you not actually encounter it and you don't.
Here it's not explicitly dealt with at the local planning level. There is a more limited form of guarantee because this is a hierarchical approach, you have a low-level model predictive controller that's countering that aleatoric robustness. But you don't have those forms of convergence guarantee or stability guarantee for this NMPC problem. So that's something you have to be willing to sacrifice in employing this kind of approach. Yeah. In practice for this application, it doesn't typically happen. I could imagine you could invent scenarios where it is problematic. So this is another tool that you could employ if you're willing to give up some of those guarantees at a particular level in your planning hierarchy. Yeah.
I know that apparently in practice, sometimes these points are not that important. But specifically when it comes to space, I would imagine that you really kind of want to be sure that things don't go wrong, right? Because it's not so easy to send things to the Mars again.
Yeah, exactly. So for this particular application, because we're a little more risk tolerant here. Again, part of the idea is because you're hierarchical, you have at least something at the end level that is spitting out some form of guarantee. But we can tolerate this sort of like higher level planner being a little riskier in terms of stability because of that, and also because of the application. So we're operating on the interior space station, and if we do occasionally have a horrible global plan and bump into the wall, it's okay. But you don't always have that. Yeah, and so you really have to be careful about the assumptions. Yeah. Yeah. Yeah.
that you have available to use in extreme environments.
This one?
Yeah,
Yeah.
so then radiation, hardened, efficient.
Yeah.
So they will also introduce you a limitation in terms of processing and memory and whatever. So the methods that you developed were already fit into the current technological capabilities of the hardware. But thinking of what is available on literature to solve these autonomous problems, do you think there would be a benefit if we had more powerful hardware, or is this not a limiting factor at all to resolve?
More compute always is almost always helpful. So in many of these scenarios, you when implementing model predictive control, you have to be careful about time steps, number of decision variables, size of the problem you're solving. More compute lets you solve more aggressive problem formulations. So I'd say for almost all the problems I talked about here, more compute would be helpful. It's always a struggle to fit within the bound that you're trying to, the compute bound that you're trying to achieve. Sort of like this little build up here. The point I was getting at is not that the approaches that I like to focus on are always targeting this sort of platform, but just that recently we have gotten enough capable compute that these a different form of solution approaches now fall within the realm of feasibility. But these approaches, like some of these model predictive controllers and other planning control approaches, are not the most compute hungry. So you could have, for example, one thing we're typically missing is like a very capable GPU on these missions. So we're probably not going to be running like an MPPI or some zero order sampling based method, at least yet. And that's the case where if you have maybe a processor of that DMIPS per watt size or a GPU available, then you can employ a different set of more capable approaches, approaches that demand higher compute that might have that might be desirable versus some of the approaches I talked about here. Does that answer the question? Yeah. 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 LiDAR is very power hungry, is typically the limitation. There are I won't name which, but there are discussions about using LiDAR at various space agencies for future robotic autonomy missions. It would be very helpful to have LiDAR versus a stereo-based approach, but stereo is relatively low power in comparison, which is one of the main reasons why. Yeah, yeah, it would definitely help with the shadowing. Yeah, yeah. All right. Any questions online? Okay, great. I'll be up here and happy to answer any questions or chat one-on-one after too. Thank you, everybody.